Is it working, Josh? Are you all right?
Yep.
So we can get started? Oh, all right. Well, good afternoon, everyone. Let's get started. We are indeed, well, lucky to have here, and it's our pleasure indeed to have one of our emeritus professors, Professor Mike Darder. I call him still Professor Mike Darder because he's been always involved with the university and teaching at the university when I first arrived. And this was back in 1996. So I still remember that he had his room, and actually he was on sabbatical that semester, the first spring semester of 96 when I was at PO5. And, well, up until that time, I guess he was teaching always his rehab class, payment management classes, concrete. He's a world-renowned authority, international authority in all of these rehabilitated payments, highway and airport payments, and the topic of concrete payments especially. So then, obviously, he went on working on more national importance items. The most important mechanistic empirical payment design guide project happens to be ESHTO 2002, back in those days, as the leading researcher with ARIS Consultants, which eventually became, for those of you young guys, ARA, Applied Research Associates. And he was then the team leader for the concrete payment part. So actually the payment ME program that you guys are using in EPDG, he was the person behind the concrete payment part of that. So with that introduction, right now he's doing part-time work with Applied Research Associates. That's where he's been for many years now. But at the same time, if you just walk by, you will see his picture, it's his photo, as one of our emeritus professors, valued professors. And it's indeed our pleasure to bring him back to give this talk. And I'm sure he will be going over all the developments of the mechanistic empirical design of payments, the long and winding road. So with that, Mike, please take the stage.
Thank you. Thank you very much.
Yeah, I'm not going to sing it. I'm going to talk about it. So, well, Errol remembers when I came here. I always like to think for my interview in the spring of 1973, a few years early. Professor Newmark was still the head of the department, and I think I was the last one that he interviewed. And I'll never forget going into his office with Moreland Heron pulling me in almost because, you know, he was a pretty awesome guy. And sit down, you know, and he started firing questions at me like a machine gun. You ever written a proposal? Yes, sir. How many? 3. Were they successful? Yes, sir. Do you like writing proposals? Yes, sir. Do you really like writing proposals? Yes, sir. How about research? You like to do research? Have you done research? You know, and it was just like this. I mean, he grew this department into what it is, you know, the foundation for what the faculty have created since then, and just an amazing guy. So I think I learned something out of that interview. Better write a proposal before any of you guys go to have an interview for a faculty position anywhere. That's a good idea. You can say yes to that answer, that question. But anyway, okay, it's really nice to be back and hope to meet some of you a little bit after this. So, yes, we're going to talk a little about mechanistic empirical design and that long and winding road. There's a couple pictures before then. Oh, I'd love to show this. This is Air Force One that's taking off, and this is Air Force Two right here. No, actually, that's Air Force One, and that's Air Force Two. In the early 90s, President Clinton, after the re-election, and Vice President Gore came to Champaign-Urbana to give a big speech. 2 speeches, I guess. I wasn't there. So Air Force One pulled in to the airport out here, and Air Force Two behind it. Huh?
Late 90s, probably.
Yeah. Was it the late 90s? Second. It was the second term. Okay, great. Anyway, so they give the speech, come back out. Everybody climbs aboard Air Force One, start the taxi out, and guess what happened? They went right off the runway, or off the taxiway, wasn't it? Yeah. And they went really way off. I mean, that's not asphalt shoulder. That is soil out there. That's one big fat sheer failure. And what do you think this commander is thinking? He's thinking about what he's going to say at his court-martial. And then they had to, of course, they couldn't get it out. They had to unload Air Force One. So, Clinton went on to Air Force Two, kicked Gore off, and Gore went on to Air Force Three, which was waiting somewhere in case of an emergency. And so they all got out of here one way or another. But the plane, I don't know how they got this plane out. They must have jacked it up pretty much. One other thing, this was the faculty back in the 70s and 80s and part of the 90s. Probably recognize some of those faces, but you see how nicely dressed we are? Well, I should, but things were worse before that. My dad was a civil engineer. There's Barry, Ernie, Sam Carpenter. He looks like just off from Texas A&M, doesn't he? Kicked off the farm, Texas A&M farm. I'm not going to show you who I am. You don't recognize me there. But this is what my dad was a civil engineer, went to the University of Texas at Austin, and that's him. And you can see, look at these dudes. Look at those hats. Isn't that cool? Yeah, that's even better. I guess it's better. I don't know. And you know who that dude is? I don't know. I think he somehow was a dropout at Texas A&M. That's what I would call him. Anyway, and you can see even in the field, my dad worked in Southern California in a lot of construction, and he's got a white shirt and a tie on almost every day, I think, a long time ago. But anyway, that long and winding road to ME Design, and boy, has it ever been, with a lot of tombstones along the way. We started out, of course, with empirical design procedures based on experience, based on some field tests, some of those early tests done in Illinois back in the 1920s and 30s, and other places, but came the actual road test was 1958, 1960. And there was a lot of good things that came out of that, of course, some procedures that could be used, but there was also a very negative effect on highway agencies with the concept that all you need is a nomograph or, as time went on, a spreadsheet. That's all you need to design a pavement, to come up with an optimum design for multi-million-dollar projects. Now it's multi-billion-dollar projects. All you need is a nomograph, and you can come up with an optimum design. Well, we all know that's nonsense, but this attitude is still around. And so the concept of spending more money, doing more thorough evaluations and testing to find out what's there and what you're designing for, measuring traffic and all kinds of stuff, soils, it's just, we don't need to do all that, spend all that money. That attitude is still out there, and that's really unfortunate, and it's taking a generation to overcome that attitude. And the road test was the thing that contributed to it the most. I mean, it had some really good things. It was adopted by all the states, Canadian provinces, many other countries based their procedures for decades on it. Up west of Chicago on the route of Interstate 80. That's actually, Interstate 80 right there. East and west, 40 out near Ottawa. Test segments, 600 test sections. From that was developed a design guide that started out. And although there are different versions of it, and they purport to improve the procedure, that really didn't happen. It just kept gold plating a pig's ear, and there was no way to really break it up and improve it. There really wasn't. And there's so many limitations in this thing. And then at the same time, in the 60s especially, 70s, 80s, there was a huge amount of great research going on, here at Illinois especially, and a few other universities around the land, doing mechanistic and fundamental research into finite element and fatigue, permanent deformation, soil, all kinds of properties, and predicting. All that was going on around. And a few of those spilled off into design procedures on the asphalt industry and the concrete industry. And then some states, in particular here at Illinois, Professor Thompson and Berenberg were a couple that really dug into that and really made a pretty good procedure in the 80s based on more on fundamental engineering properties. But a few other states, Virginia I think was another one that did that, and from the 70s on through the 90s. But what happened was traffic kept going up, as it will, with economic growth. It has to. And if you start looking at truck flow from 98 through 2020, and we're almost there, aren't we? Look at that difference. The width is down here. 30,000 is really wide. And you can see we're approaching that. 30,000 trucks a day, 2 directions. That's basically I-5. And you see that on I-80, almost that level across, all the way across I-80. And this is some I-40, I-10. And this is probably an under-prediction. We always under-predict traffic, it seems like. We never get it right, and because we never get the economy right, do we? We don't predict the stock market. So there was a lot of push with this heavier and heavier traffic, you know, and it's not only volume, but it's weights, as you can see. Big bottles now. That's from Europe. They allow that in Europe, don't they? And the actual procedure had 1 million repetitions. So we had data right here, and we were projecting 50, 100, 200. Just you know, like a highway like the Dan Ryan is almost 400 or 500 trucks, heavy trucks. It's unbelievable. Well, you know, you have a regression equation. That's all the actual road test is a regression equation. That's it. One for concrete, one for asphalt. And then you're extrapolating hundreds of times out here. I mean, I've always joked we should revoke PE licenses of people who do design pavements out here, because you're so far out of the scope of a design procedure. What are you doing? It's insane, and it's almost irresponsible. So finally, you know, AASHTO got off. AASHTO, you know, is the states. It's the power of the state DOTs. Got off their butts, and there's so many aspects I don't want to spend, but just the inside is the road test, and the black lettering is what we desperately need. You know, instead of 1 or 2 years of climate, we're designing to 50, 60, 70, even 100 years. Some Caltrans is working on that aspect of it, of design, and many new and diverse materials. Well, it's way out of the scope, way out of the scope. So AASHTO finally got started in 1987, and the university here had a prime contract, and it was a great effort that was made by all those faculty that you saw in that picture. Procedures were developed for flexible and rigid. Somehow, all that effort got derailed by the industries. The asphalt and the concrete industry got into a big fight. Who was going to lose the most market share? You know, it was a market share. It wasn't that the technical work was bad. It was a market share. And that absolutely covered that long and winding road with a landslide. A landslide. It was blocked for about 10 years. I mean, the research was still going on. All the good research to improve things were going on, but there really wasn't a lot of progression for almost a decade. Then in 1997, another big effort started. A contractor was awarded the project. You know, it was a consulting consortium. But a few months later, a big conflict arose between the principal investigator of the project and NCHRP. And a particular staff person at NCHRP that I will not name. And they just canceled the contract. Just walked away from it, canceled it, and That went about 2 years of effort. The long and winding road, it really was. The next effort started basically a year after that. And a contract this time was awarded to ARA, who grew a whole group of University of Maryland, Arizona State University, and other whole bunch of consultants and so on. A large team. And 9 years later, after much blood, sweat, and tears, it was finally accepted by the states. Voted. It was reviewed very rigorously by many people. Many of the faculty here got to review it. And other places, it was a very rigorous review, and a lot of improvements had to be made in it, and so on. So it was an iterative process. Finally, then, it began implementation, and that's been going on now for quite a few years, actually. Some states jumped in even before that, in 02 and 03, and then started implementing it. The early versions of it back then started doing testing of materials, soils, asphalt, concrete. So it really has been, and it's been with a lot of screaming and shouting and yelling over, well, it takes, the program 15 minutes to run, and unfortunately it took the concrete about 15 minutes, the asphalt, it took about 45 minutes. That was a real mistake on our part. That almost sounded like a market share problem, which, it had nothing to do with that. But so that has been improved now, and now they're down to less than 10 minutes, I think, to make a single run on them at least, with a good fast computer with 4 so-ons. So it's implementation is proceeding pretty well. I think about a dozen states now fully implemented and running, and another dozen are working at it, another dozen are still asleep, or died up in bureaucracy or something like that. But it takes a lot of training. That's what we found. You go into a state DOT and they have folks in pavement design there out in the regions and so on that are some are younger, some are older, and the older ones haven't been exposed to a lot of this information. So it really takes about a dozen training courses over a period of 3 or 4 years to really get them up to speed. So what you're learning in this now, if you're going into the workforce and working for consultants, especially on design build, or even many consultants work for states and they licenses to use the program, all that will be very valuable to you because it'll be used more and more throughout your career. But it certainly is a lot of training to get people up to speed. There's a nice manual practice that's totally outdated, and National can't seem to get their act together to update this properly, but that's in progress, so there should be one out very quickly, which is a pretty good textbook. It doesn't have any of the software. It has all the equations and theory in it, and there's a lot of errors in there as a first edition of it. Well, how many have used the program in the room here? Raise your hand. Quite a few. Some of you haven't. I'd just like to give you just an overview of it and then show you 2 examples, one asphalt and one concrete, and kind of illustrate the consequences. Pavement design has consequences, and sometimes they're bad if it fails quickly. And anyway, this procedure, the scope of it was not to do brand new research. It was to take what's available in 1998. And that's what we tried to do. We took the technology at that time, so we've already gone a long ways past that. And also was to make it so there are subsystems, so there's components that you can replace. And so everything in here can be replaced with new stuff, new theses that you guys are doing can get put into this. As time goes on, that's happening. The reflective cracking model in here is just pure placeholder. It's an empirical equation. But now Bob Litton at TTI at Texas A&M has produced a new technology for that. And there's others dealing with friction between layers. And I'm sure, well, top-down cracking is the biggest deficiency in the whole asphalt design. That top-down cracking is still a controversial deal. It's not. We don't recommend using it in here. Actually, we don't use, when we implement this in a state, we don't recommend it that they use that because we feel that it's a little shaky, and it needs a complete redo. But anyway, so what we tried to do is put it together in components. So you have a climate component, you have materials and some construction component, you have a structural component, you have the traffic loading component, and then you have putting all that together into a mechanistic response of stress, strains, deformations, and then taking that mechanistic response and accumulating that in some way and correlating that with field cracking, permanent deformation, punch outs, all kinds of things like that, transverse low temperature cracking and other things. And that's the field correlation. And this was the these were challenges enough, but this was also a big challenge to see. This is really cause and effect. If you think about it, that's what us as engineers try to learn and understand. And the better we understand that, the better. You know, the more successful we will be. Cause and effect in our judgment, right? And if you have field cracking and you correlate that against something you think should correlate with it because it's an accumulative, highly theoretical and conceptually correct or reasonably correct, and they don't correlate, all you get is a big scatter, well, you haven't, you know, you're going down the wrong road. You're really on the wrong road. Something's wrong with your theory. So getting that to agree is a real challenge, and we'll talk a little bit more about that. And so that we can, because in the end, you really can't make use of this in design. People want to see how much cracking there's going to be, how much rutting, permanent deformation, how much transverse cracking, how many punch outs on CRC, and so forth. That's the thing that they want to see to make a judgment on how to optimize. So you have a lower first cost, maybe a higher rehab cost, or vice versa. If it's heavy traffic, you want very low second cost into the future. And you're willing to pay more money up front. Dan Ryan, very expensive compared to a farm to market road out here. So that was the goal. And the software now finally is pretty well debugged, although we just found another bug in it. Somehow the freezing index, the measure of frost depth, going into, I think, the rigid pavement committee model for smoothness, for IRI, had a bug in it. Somebody found that just recently. So never say never, I guess. But this whole thing of checking your work and correcting is really, really important in this day and age. The other thing my dad taught me, he was a construction engineer, and he was out on many jobs where big beams were brought out on bridges and viaducts and buildings, and there were errors. And you can imagine people getting fired right and left when stuff like that happens. And he told me these stories all the time. So he kept pounding into my head, check your work, check your work. You do an exam, check, go back before you walk out, check your work. And you know, with our computer age, we never hear that anywhere, do we? Yeah, it's got to be right. But believe me, you get into a lawsuit over something you screwed up, and you won't forget that. We made an error in an overlay design procedure we gave to a county in the state of Washington one time. They designed 20 overlays with that, and I think they came out a little thinner, like an inch thinner. So instead of 3 inches, it was 2 inches, and so forth. Well, they held that over our heads for almost 10 years, and it was not nice. So we finally went out, did videos of the whole thing, and discovered that there wasn't any more cracking in any of these pavements, and so they released it. But they literally held a couple $100,000 over our head just for something as ridiculous as an error in an equation in a spreadsheet that caused us to give them a thinner design. Now that, if there would have been cracking out there, we would have been really in deep trouble, even though you have professional liability. You know, that only covers so much, and your company and you will forever be remembering that. So checking your work is extremely important. I'll pass that on as one word of wisdom. But anyway, and if something doesn't look right, you can, and I saw this, the freezing index was too high, is what it was. And I saw this 3 or 4 years ago and pointed it out, and nobody listened. And I forgot about it, and because it looked wrong. It just, something looks wrong to you based on what you learned and experienced. It very well may be wrong. And so you need to pursue it and make sure. But anyway, the program, at least in our mind, is working better now, and if you find any bugs in it, we would appreciate that. Okay, so what is the basics of this? And the basics are that it's characterize a layered structure, which pavements are, and each layer has physical properties. We all know that, and we've used them in most design, even in some of the empirical design we use them. But they also have thermal and hydraulic properties, and those are just about as important. In fact, ignoring those have led to a lot of failures. Whether it's asphalt or concrete, there are aggregates and soils. There's always, for every layer, you have all these basic types of inputs. And the layered systems can be many and varied, as you can see. All kinds of flexible pavement, asphalt, with unbound materials, and some cementitious, and some stabilized or compacted. The procedure can handle a lot of different varieties like this. On the concrete side, again, it's a layered system. And that was almost a new concept in concrete pavement design, because people thought, well, it's a slab, and then there's whatever is under there is under there. It's a K value. It's a spring constant. That isn't true. That is complete nonsense. It's a layered system. It's a composite beam. And so you have friction between these layers. In asphalt pavement design, you always assume complete full friction and bonding. There's no slippage in there. You'd be considered an absolute fool if you design an asphalt pavement and put slippage plane in there. Although sometimes that happens in the field if the contractor doesn't put pack coat down or waits until it cooled, the asphalt is cold and tries to bond them together. Well, that'll be slipping and you'll get cracking within a year or two. Well, on the concrete side, there's also a lot of friction. And there's only one case where really you can lose that friction, and that's where you have a concrete or a cementitious treated base course, and then you can lose that if you try to lose it. But that friction between layers is a really big deal and contributes to the structural design of the pavement in that case. That was one of two big things on the concrete side. The other one was the thermal coefficient of expansion. That was totally new on the slab, causing curling and warping, and moisture gradients too, in addition to temperature. So there's the hydraulic component and the temperature component. And then you have your modulus of elasticity. Okay, now in terms of design, it's really designed for performance. You're trying to control critical distress types that happen, that cause roughness, that cause maintenance, that cause failure, that cause potholes. And these are the ones for flexible pavements, the bottom up, fatigue cracking, and a top down. And this was very, very confusing between these two unless you can core them and really measure and find out what it is. And I think that we calibrated, some combination of these two in the calibration work. The thermal cracking, and transverse cracking, low temperature cracking, rutting, permanent deformation, and smoothness. Those are the ones that were monitored. And there's others, there's raveling. Would be another one that you could put in here. Block cracking might be another, and so on. It's mostly load associated. There are, granted, there's the supposedly just thermal, but I think this is also maybe contributed. Loading may contribute to this, and there's some climatic environmental associated with smoothness loss or roughness in the model that's built into that and calibrated into it. But other than that, and temperature and moisture is considered in these others, but there's other distresses that create problems and require maintenance that are not involved in this design procedure. How do you handle them? Through specifications. You try to specify asphalt binders and gradations that will not block crack and ravel and strip. On the concrete side, you really want durable aggregates. You want air entrainment. You want low porosity or permeability. You know, so you have to handle that through specifications and mixed design. Eventually, as time goes on, more PhD theses will get other things into this. And that'll make it a better, more comprehensive procedure. On the concrete side, well, we have the structural fatigue cracking transverse. We actually do have joint spalling. It's an empirical model now. That needs to be improved. That's a very poor model. Faulting is the step off of the joints, creates roughness, and then smoothness. And for CRCP, we have punch outs, crack spacing, crack widths, things like that. The other one, this big one that's not missing that Professor Riesler and students have done here is longitudinal cracking. That needs to be put into this. That's a really big weakness right now in this procedure, Jeff. And an important one because there's a lot of that happening when we widen out slabs for various reasons. And it's a really big deal. Okay, well, I won't spend quite as much time on all the other stuff, but here's, you know, all the different inputs to traffic. One of these is lateral within the lane, that should say. Yeah, there's lane, you know, between lanes, but then there's lateral within the lane. That's one of the new inputs. The tractor wheelbase, that contributes to top-down cracking of a concrete slab. Speed for HMA. Slow speeds, you'll get a much lower dynamic modulus, more fatigue cracking, permanent deformation. So there's some new things in there. And you can put in the axle load distributions. And when you go to other countries, like China, we measured 160 trucks on a project, singles and tandem axles. And look at that shift from the United States. Here is single axles in the US, and here is China. China just doesn't enforce I think they have legal limits, as do many, many other countries. They might have these legal limits, but they don't enforce them, so who cares? And there's a lot of pavement failures in China. And designers basically don't know that or don't design for that because the pavements, I mean, we're adding 10,000 pounds to the average axle weight in other countries than we're doing here. So what does that mean? You think you can just ignore that and make a design work for 20 years? Cause and effect, huh? That isn't going to work. 5 years, many asphalt and concrete fail in China and in other countries. And I'll be showing you one here, well, a couple. I'll show you two in a minute. So you really need to get, you know, this kind of forces you to do that. I mean, you can assume these, but it makes it clear to you that you might need to do some measurements. Okay, now another really neat thing is that there's hundreds, almost 1,000 weather stations embedded in the software. In your student version, you don't get that opportunity, but in the real world, they're all in there. And they're all getting better, and there's a whole other aspect of that using NASA data, and that may be even better than that. So better and better is still coming. You still have to put water tables in there. You need all these are all hourly numbers, so we're analyzing on an hourly basis. The integrated climatic model, that was Barry Dempsey's thesis. He was on that picture. The professor here's pictures out there too. That's his thesis in 1969. That was Barry's thesis. Great, great contribution. Because now we put moisture in it, and not only temperature but moisture, frost line, all these things are really important, and these all contribute then to what will be the moduli of the layers, whether it's or the gradients, you know, whether it's asphalt or concrete, affects that dramatically, especially if it's unbound, any kind of unbound materials. So this this was a huge benefit, or not benefit, but component of this new design procedure. As I mentioned, with concrete, instead of the modulus, you have the thermal gradients that cause curling and warping. That's just illustrating, this is in years now. So you got winter, this is hot mix asphalt base course. Winter, summer, and so on. A huge change. And of course that affects the structure. So what we tried to do was make an incremental damage approach. And it's not, well, some of it is hour by hour. Much of it is not quite that much, monthly. But as time goes on, and as computer speeds now, even, you know, like you can imagine from 2000, the computer speeds till now. I mean, there's, I don't know what the factor would be, 10 faster. Maybe I'm really naive. Maybe it's 100. I have to ask my son. He's a computer jock. But you could now do hour by hour and simulate every hour of every day of every year for 40, 50 years, and run quickly in 10 minutes. Because every material that has any temperature or moisture or aging impact is going to change all the time. Remember that? Everything changes. That's another song to remember. And then at every point in time, you have traffic loading. You have 4 different types of axles, single, tandem, trident, quads. You have a huge axle load distribution, and you have lateral water going on. As the trucks, you know, wander down that lane, sometimes you're here, sometimes you're here, and all that affects performance. That affects rutting, and that affects fatigue cracking dramatically, both of them. And then you have traffic going up every year, you know, annual increases. You have concrete modulus keeps changing. Even the asphalt has aging in it. There is a component of that in here, but it's not very good. The top inch or something. Okay, well so that's basically, so we tried to do that and did the best possible, but it can be improved a lot. For concrete, the finite element, and then this was used to generate 1 million solutions and put into neural networks so that we got instant solutions. On the asphalt side, we couldn't convince Matt Witzak to do that. So Julia, the elastic layer, is the program, and that's one of the time-consuming things, is running that program. Calculating stresses, strains, deformation for every hour or many, many hours, an average monthly, day and night, over the whole 24 hours. And as you look at the flow, say on the asphalt side, you look at the physical properties of the binders, gradations, volumetrics, temperature and aging, seasonal. You have dynamic modulus, creep compliance, you get into the engineering, and then the responses that come out of that, and then finally you're out predicting through calibration, you're predicting the stress. On the concrete side, you can look at it just a little different. You more or less have a thermal, important inputs, you have structural kinds of inputs, you have mixed properties, and you have design properties such as joints. First time joint spacing is ever used in design is right here. First time, virtually. And the first time thermal expansion was ever used in design. The first time friction was ever used in any kind of a design procedure for an agency. So you have then the field data, the empirical side of it. We say ME, the empirical side is the laboratory and the field side. There's a lot of laboratory work in here that I just haven't had time to go into. This is the actual on the concrete side. The asphalt was a little bit less than this. 300 sections, but it spans 48 years, 37 million trucks up to that high level. A little bit better than the actual road test, 2 years and 1 million. Predicting, this is rutting. The black line there is measured. They're not all this good. But here's IRI for asphalt pavement. Here's concrete. This is cracked slabs. There's the data on showing that. And then IRI for concrete. The green is the actual measured data. So this is really, you know, this So our calibrations on these 3 slides look great. I can show you some slides that don't look so great too. But I won't. Okay, let's take a look now into 2 examples. We'll first look at an asphalt example. This is the QEW, Queen Elizabeth Way in Toronto, going, well, north. It's going right into the south of Toronto. It's a very, very big truck highway, to say the least. Many, many lanes. Well, they decided quite a number of years ago now, they decided they had to reconstruct the whole thing, that it was just completely failed. And to do that, they had to reconstruct, and they had to build detours on 2 sides of the freeway. So they built 2 lanes of detours on, say this was the freeway, 2 lanes over here going north, 2 lanes over here going south. The design build team was tasked with coming up with a 1-year design. If you're ever tasked with a 1-year design, be very careful. Especially if it's more than 100 feet long. So they designed with the 93, which is what Ontario uses forever and ever and ever. They designed a pavement 4 inches of HMA over 12 inches of unbound base. The detour opened in September. Fatigue failure began the next month. This is I've somehow lost a lot of my pictures, but this is a truck lane. Well, they're both truck lanes. There's so many trucks. And you can see the fatigue, alligator fatigue cracking, mostly bottom up, I think. And that just started profusely and going on and on and on. Well, lanes had to be closed at night after night, to patch and build emergency structural overlays to strengthen the pavement. Well, the contractor was fined big time because these design build have clauses. You close the pavement down more than so much, wow, you're in deep, pay money. You can do it, but it was so bad that, it became political, and then big lawsuits happened. Well, who screwed up? Was it the designer? Was it the contractor that built it? The materials problem? What the heck? Who's responsible for this? And so pavement design really does have consequences. If now you look at this now from a mechanistic point of view, what happened? Well, here's asphalt thickness. This is the elastic layer program. Here's our prediction of alligator cracking, but you could put strain, tensile strain at the bottom of the AC right there. And you see that, as in many classes we show this and say, well, if you're 3 or 4 inches thick, for some reason you really get a high strain in the asphalt. If you go thicker than that, it gets lower. The strain goes down, and consequently the fatigue cracking. And your subgrade can be from extremely soft to very stiff. And well, there's a difference here, yeah, but it's not, well, there is a difference. And many of these soils were down, were quite soft. So basically they had about 20% in one year, 20% of the lanes failed, which was a massive amount. So let's put this into the MEPDG. Here's the cracking percentage. This was observed, about 20%. This is what the program would predict, somewhere up in that neighborhood. So if they'd have designed this, they would have seen immediately, this ain't going to work. We got a problem. You see, there's always pressure from contractor on the designer. Build it cheap. We want profit out of this job. Build it cheap. I've had pressure put on me. Anybody who's done this has pressure. Build it cheap. Don't yield to that. Don't let those guys force you into the design that you feel is risky, because it will be risky. If they'd have even gone with 5 inches, you would cut that by 1/4 almost, or 6 inches. I mean, many states have a minimum of 6 inch for a detour, and you can see why. I mean, it's going to carry about 2 million trucks, quite reasonably, and not have much fatigue failure. So, how many projects like this are there that were designed empirically that you don't? It's a very risky procedure. Okay, here's another really interesting one. Anybody from Colombia here? Aha, you know this highway?
Yeah.
Autopista Norte? Interesting project. Doug Steele and I did a lot of the work on this. This was a design, I guess this was a design build, but the designers, no, I don't think it was a design build, but the designers were separate from the contractors. And then you had the material suppliers. And we were retained by CEMEX, which is one of the cement companies that provided. They were very worried that they were going to be part of the big lawsuit that happened over this, and they wanted to know, they didn't think that their concrete had contributed to this failure. And an English firm from the UK did the structural design of the pavement. So it's a very complicated pavement, and that, so you'll have to pay attention here, and there will be an exam after this on this, what's lane 1 and what's lane 8 and so forth, and what caused this problem. It was an old concrete pavement that had been overlaid and extended and widened. And now for this design, they actually put in some, what really was flowable fill, sand and cement. Maybe a little fly ash, I don't know, not much. But this ranged from 4 inches to 10 or 15 inches or more. And it kind of evened this up. Rather than put hot mix, which they very well should have done, because this starts eroding, as you might imagine. And, well, anyway, you can see. And now you have a lane out here. It's a little thicker, and I'll show you the details in a minute. And this has a thicker slab, but it has aggregate, and then I think this was aggregate. This was some type of an aggregate. But one thing you quickly see here is almost a bathtub. There's no really drainage. Any water that gets into any of these joints, and it will when it pours in Bogota, and it does, water is going to go down in here, and you'll see what happens in a minute. And it's going to go to here, and it's going to stop. And it's going to just start flooding. Okay, so, and the other interesting thing, you have buses, big buses, and they carry a lot of people. And then you have 3 traffic lanes in one direction. And so you got trucks and autos in this direction here. And then there's bus stations down here. It's really cool, kind of a cool design to move a lot of people. So here it is. Here's the bus lane. This lane was 8 inches thick, 21 centimeters, and 4 meters, which is a little over 13 feet. And then we had very narrow lanes, less than 11 feet. Why does width matter? Because now the loads are going to be right near the edge. Your trucks are at least 8 feet. Now you're going to have much more edge loading. What does that mean? More damage. Remember your sensitivity, you put a load on an edge, it's almost double the deflection and stress than it is in the interior. And it's all 8 inches, and then you have this outer lane that is 10 inches, it's 25 centimeters. Okay, you have this flowable fill, which is pumpable, some of it, and then you have hot mix, and then here's the old slab. So you really have a bathtub. You know, water, any water getting in here is just stuck. It isn't going to get out through the soil. It's very fine-grained soil. And I just wanted to point that out, to watch that. So the buses and the trucks are quite heavy. A lot of this traffic is on here. Here's a truck, and here is the outer lane, and this is the next lane over. What do you see? A geyser, yeah. I was sitting in the Atlanta airport terminal one day, and a big plane pulled in with a gear, came right down, right on a corner of a slab. And just as it got there, this geyser went up, just like this, and down. Literally a geyser of water came out of that pavement. There was so much water under that, and then you can see, and this is worse because this is, this is not, Barry Dempsey measured pressure under here, and it's pretty high pressure, that impact, that water hammer, I guess we would call it, is huge. And what does it do? Look at this. Look at there's the flowable fill, the base course, is now overlaying the pavement. And whenever they start replacing slabs, you can see here's your slab, your flowable fill, your asphalt, and then just a bathtub in here. And it creates then cracks, which create then corner breaks. There is dowel bars, but that was, thank God they did that, or this would be infinitely worse. And here's from the center of a slab, it really bonded well, but here, when you get near the joint, it's eroded, and you can see some of that has gone up and out of the joint. Here's a pretty thick one. So you can see how ridiculous this was to try to even up, to put the paving down, to try to even the old pavement. They didn't think about how durable this was. If they would have filled it with hot mix asphalt, I don't think we would see hardly any of these cracks. I don't think we'd see it today. But that's a little more money. You're going to be faced with that in your career all the time. Now here's just a quick, these are just the volumes of trucks. So nearly 5,000 in one direction, 8,000 in two directions. That's a lot of truck traffic. The buses, almost 2,000 in one lane. And so it's not small potatoes. It's significant truck and bus traffic. Well, after 2 years, here's the consequence. Maybe 3 years, 2 or 3 years. You've got a lot of transverse cracks and a lot of longitudinal cracks. And you have a few other bigger disasters developing from here. These spill over into corner and the shattered slabs and patches and probably spalls. These keep spilling over here. And so obviously a lot of maintenance, a lot of downtime. So we have a lot of fatigue cracking, transverse cracks, like you see right here, transverse cracks in both the bus and in the other lanes, the truck and lanes next to it. Typically at the midpoint, right in the middle of the slab. But many are located in areas with no pumping, no loss of support. They're just cracking. They're fatiguing. The majority are low severity, but they continue as time goes on with heavy loads to deteriorate into a maintenance problem. Okay? So we then took the MEPDG and started applying it lane by lane and predicting then, we did coring, material testing, FWD back calculation, flew an FWD down there and did all this testing and got a lot of information out of it, which I no time to really go into all that. Put all that into the program and lane widths, thicknesses, and all of that, so you can see all the inputs that would be required to analyze that. Now this is looking at percent cracked slabs. I think it's transverse cracks. In the bus lanes, you had a lot more cracks. I think because the buses are forced to run near the edge, and that's one for transverse. So they really crack. But I want you to just look at this pattern right here. Here's lane 8, or the outside lane, and remember that was how thick? Anybody remember? 25 centimeters, right, 10 inches. This lane is how thick? 20 centimeters, 8 inches. And so was this. Look at that pattern. And you see it over here too. Boom, boom, boom. Okay? Local university got students out there and identified which lane all the trucks were in for quite a few hours. This was the breakdown of trucks. There's the outer lane, there's the middle lane, there is the inside lane, not the bus lane. The bus lane would be the next one over. Now this is like the tollway. This is exactly what happens on the tollway. We've measured this many times. You have more trucks on the lane over than on the outside lane. Look at that, double. You double the trucks here that you do here. Same here. And you saw that reflecting in the cracks. Now that's thicker, so that's not fair, but here's the fair comparison, right here and right there. That's got double the loads. Well, you'll get more cracking, maybe not double the cracking, but more. So all that kind of matches up. So then you predict over time. So here's time, here's percent slabs cracked. Here's where all we had data was up to about 3 years. And this was it's hard to tell what's so, but here's the outer lane, we predict 0, and it was close to 0. The worst was the bus, I think we predicted that as the worst. And that's that second lane over. This is the next lane over, and that's the outer lane. So that's our projection. Now, so this is 10 inches. These are 3 inches or 8 inches, but these have different traffic loads on them, for sure. This is in the east side, and this is the west side. Geez, that's a good question. 5 meters, probably maybe 4.5 meters. It wasn't too. It was pretty good, and they actually doweled the joints. They doweled the transverse joints, and but the longitudinal hardly had any tie bars in them, and that's another thing. There's no load transfer, so we modeled that more or less as 20% or something LTE. I wish we had the data out here. And now we're out here about 10 years. That would be great to find out. You're from Columbia? Can you get us that data? Next time you go home? Yeah. Well, anyway, let's get over there. Oh, just one other thing is the longitudinal. In the bus lane, there was almost none over here. These are 11 feet wide. Once you go to 13 feet, a little over 13, and you got these big heavy wheels on these buses going down this wheel path and here, or out on the shoulder, or out on the edge, I mean, you get top down, right here. You see that. That's what Professor Riesler and a couple of students did theses on to model that, and probably some other aspects of that. And so that's what we think has contributed. There was a lot of this in the bus lane, but not out here. So that's kind of interesting. So we say, totally the designer screwed up big time. That is not sufficient for millions and millions of heavy loads, just like the Ontario thing. A major structural design mistake. And it represents itself in transverse cracking. Contributing is narrow lane widths. They probably never even thought about that. No good load transfer down that lane, because these lanes were probably placed separately. And then there was erosion, and the friction, the erosion between the slab and the base has been lost. And then truck traffic is very, very heavy. I don't know if they really measured it. And then buses, operating right near the edge of the lane. So too wide, too thin. So I won't go into all of this, just the advantages, of having a really good optimization tool, a design procedure. And we think that it'll be completely redone over the years, and that's great. Here's a big project in Utah. This was almost $2 billion. It was an old asphalt pavement built up in many layers, and we designed a bonded overlay over the top of that, and milled that so it was proper elevation, and did a very efficient design. We were able to extend from about 20 miles to 25 miles. The state gave the design build team $1.7 billion, said go as far as you can go with I-15 from this point. And so we extended, we designed from 30, we went to 40-year design, and we still gave back money, $200 million to the state. And it put 5 dowel bars in each wheel path. That saves money. Now we're down to 4 dowels in each wheel path. That saves a lot of money. Those are big dowel bars. And this is a very, very big freeway with a lot of truck traffic and so forth. This actually won the top award, the best project in the country from AASHTO in 2012. So we were very happy with that. There was a lot of really good construction and management of traffic. I think they won it on the management of traffic, really, because that was, they kept 3 lanes open all the time. Okay, if there's any questions, hopefully, not quite 2 o'clock, but I'll be happy to take any. Yeah, there's no time. So thanks. I'll be here for a while. I'll be happy to talk with anybody. Or if there's any questions right now.
Maybe we can do quick questions, and then there will be a group of students waiting to meet with you.
Okay.
It was an excellent presentation. Just a question about the the interaction between the different damage types or different failures. Are there any effort to look at how those different types of damage are interacting within each other, or was it always the summation of individual different types of damage to give us the cumulative damage?
Yeah, not to my knowledge, how they interact with each other. In other words, if you get transverse cracking, that can result in alligator cracking, fatigue, in the because now you got a no load transfer.
Is there any effort, for example, to look at this data at TPP, for example, if there is any sort of interaction between different types of distresses?
Certainly. I don't know.
Or is there
a really tough question.
something like that?
That's a good PhD exam question.
I would assume some of it's calibrated in there if you have certain distresses.
Yeah.
Present.
You remove some weaknesses through calibration.
But the way that the equation is set up, because you're adding individual contributions of distresses to the cumulative damage, so they are summation at this point.
Correct. But I think like the IRI models kind of are calibrated to the existing sections, so that interaction kind of indirectly come in.
The IRI has those distresses in there, the transverse cracks, the rutting, the fatigue cracks. They're part of the IRI equation. But then there's another factor there, a site condition, which is all kinds of other factors that we don't know about, but are there. And it's related to age and freezing index and subgrade soil content, fine content. But I don't know, that's a good question. The interaction of distresses one on another, huh?
Longitudinal.
Rutting and fatigue, you mean it's like that correlation? Yeah. Yeah, if you get fatigue cracking, rutting can accelerate. Water getting in and, that whole, and again, that would be somewhat, well, you calibrate rutting by itself. And you calibrate fatigue cracking by itself. But the two are related. So, like you say, if you calibrate rutting, there's a fatigue cracking component in there that would accelerate that. Is that what you're getting at? Yeah. Okay. That's one example. Yeah, not yet, but that's a good topic. Yeah. That's right. That's right. That might take more than 3 years. Jeff?
One of the earlier case studies you showed is one of those challenging problems you get questions on a lot when people want you to design 5-year pavements or 3-year pavements. That it's a challenging engineering problem, but maybe you could talk about the validity of the program. I mean, I think the program's valid for doing calculations, but when you get into these small design windows, where do you have to be careful?
Certainly on the level of traffic. I'm sure you don't underestimate that, but I don't know, because we have the data that it was calibrated against. Some of it we have early on data, almost all the SPS experiments are all collected from day one. So we actually have data that's 1 year, 2 years, 3 years, 5, 4. You do have that. I would say constructability of a detour maybe a little bit on the low side of quality. That would be one thing. Air voids on asphalt, maybe much more. You'd have to watch. You built the thing right. I remember all the faculty that were here in the 80s. We were asked they were moving a big nuclear power component across I-55. And so we checked out all the roads. We FWD, we tested everything. It was safe. They could do it, except we didn't test in the median. They had to take the across. Well, let's say these are 2 traffic lanes, north and southbound. The median. The contractor filled this in with aggregate and compacted it. We didn't test that. That big device got over that, started sinking, blocking the traffic. Police everywhere on a Sunday morning. It's a detour. It's a detour sort of, and it wasn't compacted. It wasn't compacted. Maybe the aggregate was compacted, but anything below that was not compacted. So what? I mean, it was like, oh my God. Luckily, they had a couple of big tractors sitting off to the side. brought those up, chained them all together, and pulled this big weight out, this huge component out of the way.
Whole life stabilization by Professor Thompson there.
Yeah, yeah. He was part of this too. He should have recognized that, shouldn't he? Oh no. Any other comments? Okay. Well, I hope that's been helpful and useful and interesting. So, you bet. Good luck in your studies. If you need any, anybody needs any help, so just email me. Feel free. Anytime. Who did?
Dave Lippert.
Oh, Dave.
He wanted to know, in Illinois and Colorado, top-down cracking and HMA has been related back to the pavement. Or maybe that's a comment.
Back to the actual pavement.
Yeah, back to the paver.
Oh, the paver. That's what he means. That's right. Segregation of aggregate in a lay-down machine due to some reasons creates a weakness, and so that with shrinkage and cool temperatures that opens up. Yeah, that's right. It's a very controversial. That's what I'm saying. People believe that that's causing it all. Others believe there's other loading. I really don't know. They've lost, what, 2 big projects have been canceled over it? It's a long and winding road.
Right.